this show on the road. Good afternoon, everybody. Oh, that was weak. Come on. We're all back here. We're ready to rock. We gotta crush this, okay? Loud as you, maybe not as loud as you possibly can, but firm, you know, with feeling. Good afternoon, everybody.
Good afternoon.
Oh, that's good. That's good. That's the right volume. Okay, because we don't want to disturb the other class. Oh, all right. The rest of the quarter is gonna be so fun. Okay, we've got cool stuff lined up. We're in the middle of area, and then from that we go surface area and volume. So we're back into actual 3D shapes. We saw how awesome those were with naming them. Now we get to do even more things, solve problems in 3 dimensions. Great stuff. If you look at the schedule, I've tried to make sure there's always like one fun, eventful thing going on each week. So it's not just sit down, solve the problem set every time. Okay, so you can look forward to that. There's something interesting happening every week. I've pushed the quizzes to Tuesdays because those are the online class days. So you guys here, you won't have the quiz on Monday. It'll be on Tuesday. You'll just do it online. Okay? That's that change up. Otherwise, most everything is fairly the same. Okay? Except now you're here. I get to actually talk to people. It's great. Which means I expect responses from people. I'm going to ask a lot of questions out to like, hey, who has the answer for this? Who has the number for that? Especially computations. Just everybody have their calculator ready so we can confirm and don't just have one person compute, right? Everybody compute and we all agree on the number, then we know it's right. Okay, with that said, let's start with, we're in section 3.2, more area formulas. Okay, we had the rectangles and the triangles from the last section. And that's pretty good. You can do a lot with rectangles and triangles. Right? Computer graphics, everything is made out of triangles, so that technically is sufficient. But this is the real world. We encounter different shapes all over the place. What do we do with all these other things here? So we've come up with some shortcut formulas to make finding these areas just as easy. Right? So we're going to go through an example of one of each all together, and then I'll leave you the rest of the time to work on the problem set, okay? So parallelograms, trapezoids, regular polygons, and circles, all starting from the same place. Let's look at the parallelogram. How would we find this area? It's almost a rectangle, but not quite, right? It's been a little slanted. It's fallen over. Somebody kicked it. Wasn't very nice. Well, usually with the rectangle area, we did length times width, or base times height. You know, I don't care what you call it, really. So we multiply 2 numbers, right? We always expect to multiply 2 numbers. Triangle had that extra 1/2 in there, but that doesn't count. That wasn't a measurement. That's a constant. It's always half. Okay. So we want to multiply 2 measurements. Shoot, they gave us 3 of them. Oh, now we got to think about this. Which 2? Does it matter? Do we just pick any 2? But let's start with that. Does it matter? Yes or no? Yes. I think we can at least look at, you don't even have to actually do the computation, but can we at least recognize that, say, 2 times 1.8 is different than 2 times 2.5, right? If we picked any 2 numbers, they're going to give us different answers. There can only be one correct area of the parallelogram. So it does matter which 2. So the question is, which 2? Which 2 do you like? (1.8) and 2. Here, let me use my laser pointer here. 1.8 times 2. Those are good numbers. Let's pick the small ones. They're next to each other. They're closer, right? This 2.5 is out here being weird. Anybody like different numbers? Or do you all agree with hers? You like hers? That's a good set. Those are some good numbers, right? They're along there. Are they going to work? What if we just had that triangle? If we were trying to find the area of that triangle there, 1.8, hey, that's the height of my triangle, good job. The 2, wait, that's the hypotenuse. You don't multiply by the hypotenuse to find the area of a triangle, do you? that number doesn't work. Yeah, the diagonal ones just don't seem to cut it. There was something important about the relationship between the two legs of this triangle that let us calculate the area correctly. What was it? What kind of relationship would you say those two sides had? What's that angle? It's a right angle. Yeah, they made a right angle with each other. Right? Think about other triangles. What happened when we had a non-right triangle? Right? Or let's go like really extreme. Really far-leaning obtuse triangle. You take, let's call this the base, and then we had to do what? We had to extend that out and draw this down to make a perpendicular height, right? Remember that? There's that key word there, perpendicular height. If it's not perpendicular, it's not the height of the triangle. It needs to be perpendicular to the base. So if we apply the same reasoning to our parallelogram friend, which two numbers are perpendicular to each other? What do you think now? Yeah. Which numbers represent sides or segments that are perpendicular to each other? (1.8) and 2.5, right? So you got this side is perpendicular to that side, as indicated with the square in the corner, right? That's what we need. Area is always found by multiplying two perpendicular measurements. If they are not perpendicular, you are not finding the correct area. Okay? We had it easy with rectangles. Everything was perpendicular. Okay? Then it got tricksy with the triangle's height. So apply those same tricks of triangle heights to the parallelogram. Say, hey, wait a minute. I need to find that perpendicular. Okay? It's a two-dimensional representation. Area is two-dimensional. So we need two dimensions, one in the x direction, one in the y direction. Right? They've got to meet at a 90-degree angle. Okay? So this 2 is just here to throw you off. Okay? Don't feel bad. It was a trap on purpose. So our area for our parallelogram is really the same formula as our area for a rectangle. It's still base times height. You just got to make sure that the height is perpendicular to the base. Okay? Otherwise, it's actually not technically a height at all. Just throw it right out. Forget that too. If you were to climb up the ramp, yeah, you've walked 2 meters, but your elevation has changed by 1.8 meters. Okay? So in this case, our area is going to be 1.8 times 2.5. Okay, everybody run that calculation. What do you get? You can use your calculator, that's fine. $4.5? Do we have a confirmation on that? Yeah, my head's nodding. Okay, good. 4.5 what's? Just meters? Meters squared. We're dealing with area, two-dimensional, power of 2. 4.5 meters squared is our area. And I am just devious enough that I will give you a multiple choice question that says, what's the area? And the options will be 4.5, 4.5m, 4.5m to the power 2, 4.5m to the 3, right? Make sure, right? Okay. Any questions on parallelograms? No? Parallelograms are easy? Relatively so? They're simple, right? I would hope if I gave you a worksheet that's just all parallelograms, find the areas of all these parallelograms, you'd be like, great, this is so simple. I know exactly how to do each and every one of these. Find the two perpendicular measurements, multiply them together, done. Right? That's the easy part. That should be the easy part. Right? The challenge is going to be when it's inside of a problem And they disguise it, they hide it, they describe, oh, I'm fencing in my yard, and my yard looks like this, except the one side is at an angle of this, and how much seed do I need to fill the space with grass, or what, laying down sod, something like that. And you're like, what the heck is going on? You got to work it out, and then you draw a picture. Okay, the yard looks like this, and it goes that way. Oh, look, it's a parallelogram, right? You find the parallelogram hiding in the problem, and then you realize, area of a parallelogram, now it's easy. I got this part. Okay? Next shape. The trapezoid. Okay. Trapezoid is trying to trick us again with 3 numbers. We know better. Huh, silly trapezoid. I know to find the area, I only multiply 2 of them. Which 2 do we like? Well, from the parallelogram, I remember Mr. Apple said, find the perpendicular ones. So this 9 right here, there's my right angle, is perpendicular to 23. So my area must be 9 times 23. Does that sound good? It doesn't sound like a bad idea. But think about what that will give you. 9 times 23 is going to also be the area of this rectangle, wouldn't it? Doesn't this blue rectangle have a base of 23 and a height of 9? Is that the area of my trapezoid? It's too big, right? We need to somehow cut off the corners here. 9 times 23 is too big. It's no good. It's not that simple. All right, Mr. Apple, you're so tricksy. I know all about trapezoids, though. I know that these 2 bases are by definition parallel to each other, and thus, if this is a right angle down here, it must be a right angle up there as well. So 9 is also perpendicular to 15. Ha! Is 9 times 15 the area of my trapezoid? Sounds a lot better, right? It's not too big? Okay, but 9 times 15 would give you the area of this rectangle, wouldn't it? Aw, shoot. Now it's too small. Y'all see that, right? Blue's too big, the purple one's too small. I need my Goldilocks rectangle that's just right in the middle, don't I? So what are we going to do? If 23 is too big and 15 was too small, how do we find that number just in the middle? What do we do for that? There's probably a word for this, right? There's a term for everything. To find the middle between 2 numbers. It'd be really convenient if it started with A, just the beginning of the alphabet. When you add 2 things up, you add them both up and divide by 2. Do we have a name for such a process? At what? Average. The average, right? You find the average of 2 numbers. You add them both up and divide by 2. Right? Doesn't that give you a big one, a small one, and the average is the middle, right? That'd be perfect if we could find the average of these 2 rectangles. We'd have our answer. The height is always the same. The difference is the bases. We need an average-sized base, right? The 23 is too big. 15 is too small. So let's add them up and divide by 2. There's our base, the one we really want. Take that average base, multiply by our height. In this case, it's 9. That'll give us the area of a rectangle that is, between the blue and the purple. And the area of that average rectangle is exactly equal to the area of our trapezoid. That's kind of neat. So this is my preferred way of writing the area of a trapezoid. add the bases, divide by 2, then multiply by height. I don't like the 1/2 times height times base 1 plus base 2. It separates the half from the bases. And it shouldn't, because the reason we have the formula the way it is because it's an average. So treat your bases like an average altogether, then multiply by height. Conceptually, it works better in my brain. If it doesn't for you, that's okay. All right, so that's all our numbers there. We have a base times a perpendicular height. It's just that our bases, the one we're actually using, is the average size of the two given. 23 plus 15 is 38. 38 divided by 2, 19. 19 times 9, 171. And what are our units? These were centimeters, so this is going to be centimeters squared. Any questions on trapezoids? If you want to trap a zoid, I recommend an EMP, just because zoids are giant robot creatures. Anybody remember that show? Okay. Kind of like Gundams. Or, no, you don't watch that either. Okay, never mind. All right, regular polygons. In this case, I'm using a pentagon, right? But it applies to any number of sides. It is regular. By definition, it's been given to me as regular, so I have already marked there. All these sides are congruent, so we can take this 18 and we can use that anywhere we need it around here. Okay. Can we find the area of a polygon that's not a rectangle, right? More than 4 sides? That's kind of different. It doesn't have one height and width to multiply. So instead, we're going to use that age-old trick. We're going to turn it into triangles. Except unlike the interior angles, we're not going to go from vertex to vertex. We're going to go from the vertices into that center point. And we're going to cut this thing up like a pie, or a pizza, if you like. Okay? And then every pizza slice is now an isosceles triangle. Right? You're looking at it funny. You don't believe me? Right? If this is truly the center, then the center is the same distance from any vertex, right? So all these blue line segments should be the same. And all these bases are the same, right? Every single one of these green are 18. So would you agree that all 5 of those sub-triangles are congruent? So if I want the area of my pentagon, isn't it just 5 times the area of a triangle? Right? And if it was a hexagon, it'd be 6 times the triangle. If an octagon, 8 times the triangle, right? Just cut up into triangles. Now all we need to do is find the area of the triangle. We already did that, right? That was the last section. We know how to find the area of a triangle. Area of a triangle is? What's that? Base times height. That was a rectangle. To get the triangle, we needed one more step. 1/2. You can times 1/2 in front or just divide the whole thing by 2. Same difference. So next question, what are the base and height of my triangle here? Yeah, in this case, they're going to be 18 and 15. right? Remember, every side here is congruent, so I can put an 18 over here, say this is 18, and now we can see directly, there's my right angle, so I need the 18 perpendicular to the 15. This now, if you turn it, tilt your head a little bit, that's the height of my triangle. All right, so let's put all this together. Let's put it in one equation. I think we can handle that. 5 times base 18 times height 15 divided by 2. There we have it. And I like putting it all together because I can usually simplify a little bit ahead of time. You can type that in the calculator just as is, that's fine. I'm going to look at that 18 and say, hey, 18 is an even number. It divides by 2, and that gives me 9. Now I only have to do 5 times 9 times 15 in the calculator. Save myself a step, right? What's that equal to? Landry, you got a number? What? I did the divide by 2. Right? I simplified the 18 with the 2 to get 9. That's just a mental math. Again, not necessary. You could do 5 times 18 times 15 divided by 2 all together in your calculator, or if I did this, just 5 times 9 times 15. You don't have your calculator out. Somebody who has it. You've got it? 675 inches squared. Do we agree? Yes. Very good. This is how I deal with regular polygons every time. I mentally break it up into triangles. It's most convenient for me. However, the textbook went one step further. They pointed out, hey, wait a minute. If you take the side length and you're going to multiply by the number of sides anyway, isn't that just the perimeter of the whole shape? And be like, yeah, textbook, that's a good point. So we could simplify this and say the area is, here, let me do this in purple. The area is the perimeter times that height, although it's not the height of a triangle anymore, and it's not the height of the pentagon, but they came up with a different word for this line segment that goes from the center perpendicularly out to a side. Anybody remember what that was? It also started with an A. That's okay. It's called the apothem. Okay? This is a fancy term for this kind of segment, right? Perpendicular to the side, up to the middle of the polygon is the apothem. It looks kind of like the radius of a circle, doesn't it? We're used to that one. We know a radius. So the radius, not really, the apothem of the polygon. In this case, it's 15. That's all right. So we can take the perimeter times the apothem divided by 2. Right? And that's combining everything there. We just took the 5 and the 18 together. That gives us perimeter. 15 is our apothem, still divide by 2. So that formula works as well. It's a handy shortcut if you want to use it. As I said, I typically don't, just because usually I'm not given the perimeter. I'm usually given a side length. Okay? And so mentally, I just walk through this whole process and be like, oh yeah, think of it as triangles, create my equation from there. Since I got to calculate the perimeter by hand anyway, I don't see it as much of a savings to start with this equation. But if you are given the perimeter, do realize, hey, there's a shortcut there. Okay, so good to have as reference, not needed to memorize. Questions about a regular polygon? Okay, we got one more to do. The circle. And the circle is almost like a special case of the regular polygon. It's a polygon reaching infinite sides. And so the area equation was a special case. Anyone remember what it was? When I say remember, I mean, did you write it down in your notes and you can look it up? Area of a circle should be there. Say again? Pi r square. No, they're not. Pi are round. When have you ever had an apple pie in a square dish? Come on. Rounded dish. That's a joke. Okay, forget it. Pi r square. That's exactly right. I can write a better r there. Area of the circle is pi r square. Okay? Except I thought one circle was too simple for an example. Let's do a double circle. We don't want the area of just a circle. We want the area of the donut between the two circles, right? This is a very common tactic, right? Very often you'll find the area between something. Right? And so it's good to remember that the area between two shapes is simply the area of the big shape minus the area of the small shape. All you have to do is subtract. Okay? If we find the big circle area and take out the donut hole, right, remove the little area, what's left is just the shaded bit in the middle. So just like we could add up areas to get the whole conglomerate shape, we can also subtract off things we don't need. That's a very useful tool to have. Okay? So in this case, our area is going to be the difference of two circles. So we need the, looks like the, I'm going to call them the 10-foot circle minus the 3-foot circle. Just use a little subscript there to reference which one is which. And now we just got to put in our actual circle area formula, right? For each one. So first we have pi times, that radius is 10 squared, minus the second circle, the small one, is pi times the radius of 3 squared. And I want you to write it as one equation. Okay? You could, yes, compute the big circle, get a number, done. Compute the small circle, get a number, done, then subtract them. That's the elementary student approach. Okay? We're in high school. We've got some algebra under our belts. Let's use that algebra to our advantage. Okay? By writing it as one big equation, it's a little bit scarier looking. Okay? Trust me, they can get worse. But there's two big advantages to doing so. One, sometimes you can make things easier. They'll simplify out. Like what I did with the pentagon here, right? Writing it all as one, I can see, oh, look, these numbers relate, and I can reduce and simplify. Make things easier for yourself. So if you write it the long way, you can sometimes make it easier. Second, we can sometimes make it more accurate, particularly with area estimates, particularly with circles, because pi is involved. And we don't have an exact number for pi. Well, we do. It's called pi, right? So whenever you want an actual decimal, 3.14159, you got to round off somewhere, right? The more rounding you do, the less accurate your answer. So right now, as is, I could put it in my calculator, pi times 10 squared, and then subtract pi times 3 squared, and I can type pi twice. We could do that. But it'd be better if we'd only had to use the pi button once, wouldn't it? Then I'm not adding two rounded numbers, I'm only rounding my final result. Written as this, we can bring in a little algebra, sneaky, and factor out the pi. Aha, it's pi times the quantity, 10 squared minus 3 squared. Now I only have to use pi once, thus improving my accuracy. And I think it makes it a little bit easier because these I can do in my head, right? This is just pi times 10 squared, everybody. 100. 3 squared, everybody. 9. And 100 minus 9, everybody. 91 times pi. Remember, until the very end, we can just treat pi like a variable, right? You can factor it out just like x. And we put it after the integer numbers, just like we would with x. Okay? It just looks a little cleaner that way. That's our perfect, precise, exact answer. We still need units, though. What are the units on this? They're not inches. This one's feet. Okay? 1 tick mark means feet. 2 tick marks means inches. Okay? That's good to know. I think it comes from engineers who are sometimes even lazier than mathematicians. They got tired of writing out inches and feet. Okay? 2 letters was not short enough for them, so tick marks all around. Okay. And when you start like measuring pipes, all day long, and you gotta mark what is what, like, you'll appreciate this. Yeah. Okay, so those were in feet. So our final answer is 91 pi, what's feet squared? Now, if you go to the carpet guy and you say, hey, I need to purchase 91 pi feet squared of carpet, they'd be like, you want what now? Right? They can't measure that off the roll. We need an actual decimal approximation for any real world application. So let's get a decimal approximation, right? Go ahead, type in 91 times pi in your calculator. What do you get? Give me to 2 decimal places. It's about almost 300, right? 200 something? What is it? $85.88. 8 squared. Okay. And let's call both of those the answer. All right. My preference is to include both. Right? When in doubt, just give both of them. Right? We've got the perfect exact mathematical answer. Okay? That if whatever the context is, we need more decimal places, we can always reapproximate that by a better version of pi. Okay? If we have more computations to do, if there's a part B, part C to the problem, okay? We needed this first. Stop, report that answer. Now use it, maintain accuracy as long as possible. But when it comes to the application bit, we have an actual number that makes sense in our brains. Be like, oh yeah, 285. I can understand about how much that is. Right? 91 pi, that sounds like a stack of pies, and it would, take me several months to eat through them. It'd be great. It's about a year's worth, I would say, at least. Okay, any questions on circles? No? All right, then, as always, we've got 3 levels of problems for you. Level 1's most of the basics, 2 is a little more practice, and 3 is usually the trixier ones or just ran out of time, so they're very interesting. Please read through them at least, just to check them out. Most of the first ones are the practice. We're getting most of the basics out of the way. Okay? We need that repetition, get that practice in so that parallelograms and trapezoids, finding those areas is easy peasy. And then on Wednesday, we get the much more interesting problems. Like, okay, well now apply it to this context. And the context is the fun part. The computation just comes naturally. But I did throw one nice application one in here in the level 1, and that is with area of pizzas. Okay? And this is a great thing you might actually want to do for yourself, is how to get the most pizza for your dollar. Okay? We're all frugal people in here. We want to save money where we can, but I also want as much pizza as possible, right? That applies to everybody in this room, I would think. Yeah? And so we're going to actually look at, okay, what are the area and how much pizza per dollar do you get with the different sizes, so that next time when you order Domino's, maybe the large isn't always the best option, right? You got to compare the sales and work it out, right? So there's a little practice there for you. All right? And I think with that, when is class actually over today? 35? Okay, you've got 5 more minutes.